For today's math lesson, we're going to be working on solving one-step equations. So equations that only have one step, and specifically, we're going to be looking at equations that involve both whole numbers and decimals that are either positive or negative. So the first thing I'll do is just go over a couple key ideas, and the key idea I have for you today is two words, and those words are inverse operations. You've probably heard that before, but we're going to take a minute to make some sense of what that means because it'll be useful going forward for our next few lessons. So inverse operations, all that means is inverse operations undo one another. So let's take it out of math context for a second. If I were to tie my shoes, the inverse operation to that is untie my shoes. It's undoing a tied shoe. In math, every mathematical operation, addition, subtraction, multiplication, and division, they all have inverse operations, things that undo them. And we use inverse operations when we are solving equations. And inverse operations is going to be used in every aspect of math when you are solving. So when you get to Algebra 1, Algebra 2, trig, and beyond, you're going to be using the concept of inverse operations. So it's a good idea to try to internalize what this means now. So the goal of when you solve an equation, ultimately, what do you want? You want to find out what x equals, or p, or t, or whatever variable it is. At the end of the day, you want your equation to say x equals blah, and blah is the final answer, the solution to the equation. To get to that final step of the equation where it says x equals blah, we need to get rid of all the other parts of the equation. And when I say get rid of, we need to inverse them out. You can't just simply take things away. There is a mathematical way to do that, and it's by inversing whatever operation is occurring. That will get rid of what's there. So we're going to use inverse operations, and the way that I typically explain this is by thinking of one of these. This is a scale. This is a picture of a toy one. My kids have one like this. But a scale, what happens? When you put something on one side of the scale, it's going to tilt unless you put the same thing on the other side. Likewise, if you were to remove something from one side of the scale, it's going to tilt unless you remove the exact same thing from the other side. And an equation works the same way. So let's take a super duper basic equation. Let's do x plus 3 equals 5. Now, before you sit there and say, oh, x equals 2, I already know it's got to be a 2. Sometimes you can mentally just see it, but I'm using a small example because this is how it works for every single equation. So if you can understand this little example, you can understand any example. So just like this scale has two sides, and then there's like a middle, every equation has two sides. And the sides are separated by the equal sign. So envision this is our scale. And to start, every time you start an equation, it's balanced. It's like this scale up here. Everything is perfectly equal. This side is equal to this side. The problem is sometimes you have an unknown part of your equation, and you're not sure what's making this balanced. Why is this balanced? And so you use inverse operations to figure out what that missing thing is so that you can understand what balances the equation. Like I said, sometimes you can just mentally see it because the problem is very simple, but we're going to use a simple one because it works for all equations. So ultimately, what do I want? I want x equals something. I want to know what is this unknown thing that's balancing the equation. And so I need to get rid of everything else in the problem. So all that remains is the x, the equal sign, and then the solution. So I need to get rid of this 3 because right now it's with the x. And I just want it to say x equals, not x plus 3 equals. So how do you get rid of plus 3? What's the inverse of adding 3? Well, I had said previously, every operation has an inverse, something that undoes it. How do you undo addition? You subtract. So the inverse operation here is subtract. So I am going to, on this side of the equation, subtract 3. Minus 3. Now, think of our balance. If I took 3 off of this side, would the scale still be balanced? No, it wouldn't. How would I keep it balanced? I would take 3 off of this side as well. So the key concept in all of this is that whatever you do to one side of your equation, you have to match it on the other side so that the scale, so to speak, stays balanced. So if I'm taking 3 off of this side, I'm taking 3 off of this side as well. Now, when I do plus 3 minus 3, those are inverse operations, so they cancel out. And what's left is x, because I got rid of the plus 3. And now we're at equals. And then on my right side of the equation, 5 minus 3 is 2. And I've gotten to where I want to get. This was a one-step equation, and the one inverse operation was to subtract 3. And it got me to x equals 2. That's my solution, which we probably already knew going into this because this was an easy example, but that's how it works. You inverse, and you get to your solution. So let's look at a couple of other examples, and then that'll be it for today. In this example, there is one operation, right? This is a one-step equation. I ultimately want to get x equals something, so I need to get rid of this other stuff in the problem. Well, what's the inverse? How do I get rid of minus 5? The inverse of minus 5 is plus 5. Inverse operations cancel out, and whatever you do to one side of your balance, you have to do to the other side so that things don't get out of whack. So I've gotten rid of this. Now I'm down to x equals, and now the only work I need to do is what is negative 1 plus 5, because that's what we're doing on the right side of the equation. Negative 1 plus 5 is 4, and that is my solution. And the beauty of problems like these is you don't need anyone to tell you if you're right. You can know just by taking that final solution and plugging it back in and testing it out. Is 4 minus 5 equal to negative 1? It is, and therefore I have found the definite solution. It has to be 4. That's the only thing that's going to make this thing balanced and true. All right, next example. Example 2, we've got k plus 8 4/10 equals negative 6 3/10. So ultimately, just to center what we're doing, we want to get k equals something. And so I need to get rid of the plus 8.4 so that I have k isolated by itself. So how do you get rid of plus 8.4? Well, the inverse to that is to subtract 8.4. Inverse operations cancel each other out. So now I'm down to k equals, and the only thing I have to remember is whatever you do to one side, you do to the other. So I'm going to subtract 8.4 on the right side of my equation. So now all I need to do is what is negative 6 3/10 minus 8 4/10. And if you can remember, anytime you're subtracting with negative numbers, a good thing to do is rewrite the problem as an addition problem. You add the opposite. So this is really just negative 6.3 plus negative 8.4. So the final solution here should be negative 14.7. Negative 14 7/10 is what k is equal to. When you're adding two negative numbers, just forget that they're negative, add them together, and two negatives added together just become a smaller negative number. All right, last example for today. W plus 13 2/10 is equal to 10 4/10. So the inverse here, you should know, is going to be to subtract. That's the opposite of adding 13.2. And whatever I do to one side, I do to the other. So now I have W on the left side equals, and I'm going to be doing 10 4/10 minus 13.2, which could be rewritten as 10 4/10 plus negative 13.2. So now for this addition problem, I'm adding one negative and one positive. When you have one of each, you just find the difference between the two. And then you keep the sign of whichever number has a larger absolute value. So 13.2 is bigger than 10.4. So I know my final answer is going to be negative because this is negative. So there's like more negatives than positives. So let's subtract here and we get 2 and 8/10. So the final answer here should be negative 2 and 8/10. W is equal to negative 2 and 8/10. And that makes sense, right? If I'm at 13 and I need to get down to 10, I need to add a negative to it to bring it down. And so this answer is totally reasonable. And that's our lesson for today. Go slow, show your work. And when I say show your work, I mean show your original problem. So that would be this line. Show your inverse operation, whatever it may be, and then get down to variable equals blah, circle that final answer. And any scratch work you need, just do it on the side, similar to what I did for all of these example problems. If you have questions, reach out. Otherwise, happy solving, happy mathing. Bye-bye.